Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on theory of numbers, lecture number 1, in which I will discuss on divisibility and division algorithm. Now we discuss about divisibility. Let A and B be two integers, Z be the set of integers, and A not equal to 0. Then B is said to be divisible by A if there exists an integer x belongs to Z such that B equal to AX. Here we denote this by A divides B. If A is greater than 0 and less than B, then we say that A is proper divisor of B. We call this concept by number 1, A is a divisor of B. A is a divisor of B. Number 2, A divides B. Number 3, B is a multiple of A. Now we prove a theorem. Theorem is A divides B implies A divides B.Sc for any integer C. Here A, B, C are integer, means belong to Z. Z be the set of integers. Given that A divides B, from the definition we know that this means B equal to AX, X belongs to Z. Let this is number 1. Implies that B.Sc equal to AX.C equal to A.X.C associative law for integers. This is number 2. Since X, C both are integers, implies that their product is also integer. Let XC equal to Y. This is number 3. From 2 and 3 we get B.Sc equal to AY. Y belongs to Z. Implies that A divides B.Sc from the definition of divisibility. Proved. Now we prove the next theorem. A divides B and B divides C imply A divides C. Let A, B, C belong to Z. Z be the set of integer. Given that A divides B, From the definition of divisibility, B equal to AX, X belongs to Z. Let this is number 1. Again, given that B divides C implies that C equal to BY, Y belongs to Z. This is number 2. Equal to, by using 1, B equal to AX. So here we write AX Y using 1. This equal to A XY under bracket. By associative law of integers, this is number 3. Since X, Y belong to Z implies that their product X, Y belong to Z. Let X, Y equal to P. P belongs to Z. Therefore, using 4 in theory, we get C equal to AP, P belongs to Z, implies that A divide C. Proved. Now we prove the next theorem. A divides B, A divides C, imply A divides Bx plus Cy for any integers x and y. Given that A, B, C belong to Z, these are integers. Also given that A divides B implies that B equal to AP, P belongs to Z. This is number 1. Again, given that A divides C implies that C equal to AQ, Q belongs to Z. This is number 2. Now, X, Y belong to Z and Bx plus Cy equal to B means AP from 1, AP X, and from 2 C equal to AQ, AQ Y. This equal to A PX by associative law plus A QY by associative law, and by distributive law A PX plus QY. This is number 3. Since P, Q, X, Y belong to Z integers, implies that Px is an integer belong to Z and Qy is another integer. Addition of two integer is integer, therefore Px plus Qy belong to Z. Let Px plus Qy equal to R belong to Z. This is number 4. Using 4 in theory, we get Bx plus Cy equal to AR. R belongs to Z, implies that A divides Bx plus Cy. Proved. Now we prove the next theorem. A divides B and B divides A, imply A equal to plus minus B. Given that A, B belong to Z integers and also given that A divides B, implies that B equal to AX from the definition of divisibility. X belongs to Z. This is number 1. Again, given that B divides A, implies that A equal to BY. Y belongs to Z. This is also from the definition of divisibility. Now, using 1 in 2, this equal to, in place of B we write AX. AX Y. Associative law. A XY. This is number 3. Since A equal to AXY, that means XY must be equal to 1. Therefore, from 3, XY equal to 1, which is only possible when number 1, X equal to 1, Y equal to 1. Number 2, X equal to minus 1, Y equal to minus 1. Therefore, by taking Y equal to 1 and minus 1 and putting in 2, we get A equal to B plus minus 1, implies that A equal to plus minus B. Proved. Now we prove the next theorem. A divides B, A greater than 0, B greater than 0, imply A less than equal to B. Given that AB belong to Z, Z be the integer, set of integers, and A greater than 0, B greater than 0. Also given that A divides B, from the definition of divisibility, B equal to AX. X belongs to Z. This is number 1. Since A greater than 0, B greater than 0, therefore from 1 we get X greater than 0. Means left side is positive, then right side is positive. A is positive, then X must be positive. This is number 2. Since X is an integer and X greater than 0, that means X greater than equal to 1. This is number 3. If X equal to 1, then from 1 we get B equal to A multiply 1, implies that B equal to A. This is number 4. If X greater than 1, then from 1 we get B greater than A because X is greater than 1. This is number 5. Therefore, from 4 and 5, we get that B greater than equal to A. Implies that A less than equal to B. Proved. Now we prove the next theorem. If M not equal to 0, A divides B implies and is implied by MA divides MB. Since given that A, B, M belong to Z, Z be the set of integers, and M not equal to 0. Given that A divides B, therefore by definition of divisibility, B equal to AX, X belongs to Z. Since M not equal to 0, then MB equal to MAX. Since M not equal to 0, implies that MB equal to MAX by associative law. Implies that MA divides MB since X belongs to Z. First part proved. Conversely, let MA divides MB and M not equal to 0 implies that MB equal to MAY. Y belongs to Z. Implies that MB equal to, by associative law, MAY. Y belongs to Z. And since M is not equal to 0, then cancellation law holds. Implies that B equal to AY since M is not equal to 0. Here Y belongs to Z. Therefore, this means A divides B. Proved. Now we discuss about the division algorithm. Theorem. Given any integers A and B with A greater than 0, there exist unique integers Q and R such that B equal to QA plus R, where R greater than equal to 0, less than A. If A does not divide B, then R satisfies the stronger inequality R is greater than 0, less than A. Now we prove this. Now let we consider an arithmetic progression as B, B plus A, B plus 2A, B plus 3A dot 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 in right side, in left side b minus a, b minus 2a, dot 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 dot, extended indefinitely in right side as well as left side. Here common difference is a. In this sequence we get the smallest non-negative integer. Let that integer is r, and r will be greater than equal to 0. It may be possible that r equal to 0, and if it is not 0, then non-negative means positive, then r will be a positive integer, but r must be less than a, as a greater than 0 here. So r will be of the form b minus qa equal to r. Q belongs to z. Here we see that b minus 2a, b minus 3a, b minus 4a, and right side also b plus a, b plus 2a. Therefore q must be an integer. Implies that b equal to qa plus r. This is number 1. Now we examine the uniqueness of this structure b equal to qa plus r. If possible, let q1 and r1 be another pair such that b equal to q1a plus r1, r1 is greater than equal to 0 and less than a. Let this is number 2. Without loss of generality, let we consider r1 is greater than r. That is, r is less than r1, implies that r1 minus r greater than 0. Let this is number 3. r1 is less than a, r is less than a means r1 minus r greater than equal to 0 and less than a. This is number 4. From 1 and 2 we get qa plus r equal to q1a plus r1, implies that a q minus q1 equal to r1 minus r. Let this is number 5. If q minus q1 equal to 0, implies that if this is 0, left side 0, then right side 0. r1 minus r equal to 0 implies that r1 equal to r. This is number 6. If q minus q1 not equal to 0, and since q1 belongs to z, implies that q minus q1 belongs to z. Therefore from 5 we get a multiplied by an integer equal to r1 minus r. That means by divisibility definition, a divides r1 minus r. This is number 7. Since a greater than 0 and r1 minus r greater than 0, here in theory, from 7 we get a less than r1 minus r. This is 8. Here in 4 we see that r1 minus r less than a. In 8 we see that r1 minus r greater than a. Therefore we get contradiction. Therefore our assumption q minus q1 not equal to 0 is not a possible case. That is, q minus q1 equal to 0 is only possible case. In this case, we get q equal to q1 and r equal to r1. That is, q1 equal to q and r1 equal to r. Therefore, q1 and r1 are not another different pair. Therefore, b equal to qa plus r is unique representation. Proved. Now, I will give you details of my lecture notes. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.